Good morning, champ. Now we're tying everything together. We've learned how to take partial derivatives and how to organize them into the Jacobian matrix. Now it's time for one of the most powerful ideas in multivariable calculus, the generalized or multivariable chain rule. Just like in single variable calculus, where the chain rule links the rate of one change to another, the multivariable version tells us how to handle compositions of functions that depend on several variables. Let's start simple. Suppose we have z equals f of x and y, but x and y both depend on a single variable t, then z also depends on t. The chain rule says dz by dt equals partial f by partial x times dx by dt plus partial f by partial y times dy by dt. In words, the total rate of change of z is the sum of how z changes when x changes plus how z changes when y changes, each weighted by how fast x and y move with respect to t. In short, follow each path of dependence and multiply the slopes. Now for the general case. Suppose z equals f of x and y again, but x and y depend on two new variables, u and v. Then z is really a function of u and v. The chain rule says partial z by partial u equals partial f by partial x times partial x by partial u plus partial f by partial y times partial y by partial u. And similarly, partial z by partial v equals partial f by partial x times partial x by partial v plus partial f by partial y times partial y by partial v. Each derivative of z with respect to an outer variable is a weighted sum of all the ways the inner variables influence it. Here's a visual way to think about it. Imagine u and v feeding into x and y, which then feed into z. Each arrow is a path of dependence, and the chain rule says to multiply along each path and add everything up. Now, let's make it concrete with a classic example. Polar coordinates. Take z equals x squared y plus sine of x, and let x equal r cosine theta, y equal r sine theta. We want to find how z changes with respect to r and theta. Step 1. Compute the outer partials. Partial z by partial x equals 2xy plus cosine x, and partial z by partial y equals x squared. Step 2. The inner partials. Partial x by partial r equals cosine theta. Partial y by partial r equals sine theta. Partial x by partial theta equals negative r sine theta. And partial y by partial theta equals r cosine theta. Step 3. Combine them. Partial z by partial r equals open parenthesis 2xy plus cosine x close parenthesis times cosine theta plus x squared times sine theta. And partial z by partial theta equals open parenthesis 2xy plus cosine x close parenthesis times negative r sine theta plus x squared times r cosine theta. That's the multivariable chain rule in full action. Each outer partial multiplied by the derivative of its inner variable, summed over all the paths. In higher dimensions, we can write this compactly using Jacobian matrices. Suppose capital F maps Rn to Rm and capital G maps Rk to Rn. Then the composition F circle G maps Rk to Rm. The chain rule says the Jacobian of f circle g at u equals the Jacobian of f evaluated at g of u multiplied by the Jacobian of g at u. In short, Jacobians multiply. The derivative of a composition is the product of the individual derivatives, just like the single variable chain rule, but now in matrix form. Geometrically, each Jacobian acts as a local linear transformation. When you compose functions, you apply one transformation after another. So, multiplying Jacobians is like chaining together local scalings, rotations, and stretches of space. The total transformation is their product. Let's summarize. 1. The partial chain rule means we sum over all paths of dependence. 2. In matrix form, we multiply the Jacobians. 3. The determinant of the composition's Jacobian equals the product of determinants, the total scaling factor. 4. Geometrically, each function locally transforms space, and the composition stacks those transformations. And the key idea: change propagates through every link in the dependency network.